You'll find it hiding in shadows.
Hello and welcome to the video on the definite integral. So in a previous section, we learned that the limit as n goes to infinity of the right endpoint approximation, as well as the limit as n goes to infinity of the left endpoint approximation, and the limit as n goes to infinity of finally the midpoint approximation, all go to the same place, right? They should all approach L when f of x is a continuous function. So, building off of this, we can learn about something else called a Riemann sums. Riemann sums. Okay, so this is actually another kind of approximation, all right? And these are more general kinds. So, more general approximations than even the right endpoint, left endpoint, or midpoint, because our partitions, or the subintervals, so the partitions are divided, they divide our interval AB, our full interval, into n subintervals, just like the other ones do, right? The other approximations we've learned about. But this one, this Riemann sums, they don't have to be necessarily of equal width. Not necessarily. They can be if you want them to be. Then it'll just be your right or left or midpoint approximation. But anyways, they don't necessarily have to be of equal width. Okay, so that means that we could just chop it like here's a graph, let's say. So here's our x and y, and then we have something like this, okay? And then here's our a and b, and instead of doing equal, we could divide it into something like this. Then we'll make one of them really tiny, and then we'll do another one kind of randomly, like that. So we could have like 4 subintervals that are not of equal width. Okay, and then we also have sample points. So our sample points aren't necessarily on the right for like right endpoint or left endpoint. They're not all like that. Our sample points are called C, and they consist of C sub I, or C sub 1, sorry, C sub 1, C sub 2, etc. up to C sub n, for however many n subintervals you have. And there's one in each subinterval. And it doesn't necessarily, they don't all have to be in the same location on that subinterval. They don't all have to be midpoint or all right or all left. They're just somewhere in there, okay? Alright, so anyways, let's expand off of this topic on the next slide. So let's say that we have, here I'll draw a bigger graph, okay? So we have x and y. Alright, and then we have some curve like this, let's say. Okay, so here's our A, and here's our B. And let's say we have 1, here's x sub 1, here's our x sub 2, that's a little bit further, let's say. And here's x sub 3, that's kind of close there. Okay? And then this is like, B is like our x sub 4, and A is like our x sub 0, or x naught. Okay? So basically, the length of our subintervals are, so length of sub interval, okay, I'll abbreviate, is basically delta x sub I, where that is equal to x sub I minus x sub I minus 1. So what that means is if we were to try to find the length, so delta of our first subinterval, we would say x sub 1 minus x sub 0. So in this case, that would be x sub 1 minus x sub 0, so this is our delta x1, okay? Then this would be our delta x2, and so on and so forth, okay? So that's our delta x, those are the lengths of our subinterval, and a little terminology, something denoted by this is called our norm, okay? So norm is basically the maximum, or the greatest, I'll just put maximum here, the maximum length of our subinterval, x sub I length. Okay, so whatever our greatest subinterval is, so in this case, mine would be this one right here. This is a delta of x sub 2. Okay, so this would be the norm, all right, because that's the greatest subinterval that I have in my interval from A to B. Okay, so also something to note is that we have within each sample point, so with, well, let's construct our sample points first of all. So in here, let me continue. So we have x delta x sub 3, and lastly our delta x sub 4, because I made 4 subintervals here. And now what we're going to do is pick a sample point within each of these. So again, like I said, our sample points don't all have to be in the same spot on our intervals. We can pick one, let's say C1 is here, C sub 1 is there. We'll make c sub 2 be a little bit more to the right on this one, so this is c sub 2. Let's say c sub 3 is smack in the middle there, c sub 3, and finally c sub 4 is somewhere over here. Okay, so c sub 4. Alright, so those are the points in our intervals. See how they're all kind of like randomly placed, basically. But anyways, so what we're going to do with each of those sample points, so with each c sub I, that just means our sample points in the interval, we're going to construct a triangle, or a rectangle, sorry. So we construct a rectangle, and I'll just put a drawing of a rectangle there. We're going to construct a rectangle. Well, actually, the rectangle looks more like that. Anyways, so we're going to construct a rectangle with the base being our delta x sub I, and the height being height of f of c sub I. Okay, so basically that means our base is going to be that. So for example, our first rectangle is going to be the base is here, right? So that's the length of delta x sub 1. And then what this means, f of c sub I, that means the value of our function, so this is our f of x, evaluated at that sample point. So we're going to take c sub 1, draw a line straight up. So that's the same thing as plugging c sub 1 into our f of x. So we're going to evaluate it there, and that will be the height of this rectangle here. So we're going to draw that straight across. So here is our first rectangle, okay? And for the second rectangle, what we would do is take this base, so that would be delta x sub 2, right? That's the length. And then we're going to take c sub 2, our sample point, draw our line straight up, just like we're plugging that value into our f of x. We're going to create our rectangle there, okay? And then we'll do the same thing for the next ones. We have this rectangle here, take c sub 3, draw a line straight up. That's kind of even with the other rectangle. And lastly, c sub 4. This one's a little bit higher, okay? So then we're going to draw a line straight across and create that last rectangle, okay? So that's basically it, and then we're going to take the area of each of those and add them together, okay? So our formula here for the Riemann sums, so I'll write Riemann sums. So the overall formula is going to kind of look similar. It'll look familiar because the area, so area of one rectangle, one of those rectangles of our subintervals, rectangle, is going to equal the base, right? So that's the length of the subinterval on the bottom, and then times the value of our function evaluated at the sample point within that subinterval. Okay, so that's the area of one rectangle. So therefore, our Riemann sums, which is denoted by this fancy notation, are of f, comma p, comma c, and I'm not entirely sure what all of those mean, but this means the function, I believe. This is the p, maybe the norm, like the longest subinterval, and c means sample point, possibly. So anyways, this is going to be equal to, that just means Riemann, okay? The sum of, as I goes from 1 up to n, of f times, f of c sub I, and then times that delta of x sub I. So basically this, I just kind of switched the order there. And that's pretty much it. So this means that we're going to take f of c sub 1 times f of, So f of c sub 1 times delta x sub 1 plus f of c sub 2 times delta x sub 2 plus ... and then all the way up to f of c sub n, and then times delta x sub n. Okay, so that's basically it. And again, this is just more for your own reference or understanding. There's kind of just like an offshoot of the right and left endpoint approximations and the midpoint approximations. Okay, so building off of this though, this is important for your understanding, like I said, because it leads us into something called integration.
If that's the way it is, then that's the way it is. I still feel